Hello, here's another video from Mr. Mitchell. Why don't you write down these questions and we'll talk a little bit about radioactivity. You've heard of radioactivity. You've seen signs and seen in movies and just generally probably know that the reputation of radioactive material is that it's dangerous, and it is. But what exactly does it mean to have an element that is radioactive? Well, it goes down to the subatomic level. Yes, it has to do with the nucleus of a radioactive element. You see, the nucleus, that's where the protons and neutrons are, on most elements are very stable. But that's not the case for radioactive materials. What happens with radioactive materials is their nucleus suddenly will emit particles and just send them out flying in whatever direction. And since it sends out these particles can combine with things that they go through and completely change what it is, or just the speed of these particles can act, well, kind of like a wrecking ball, you might say. And that's part of what makes radioactive materials dangerous. Now, an isotope or completely different element can form, or you can just have the damage. And whenever you have the nucleus shooting out materials, it's called nuclear decay. That's the decay of the nucleus of a radioactive material. And anything that is released, like whatever material this is what's called radiation, nuclear radiation. Now, don't get this confused with the radiational heat from the sun. You know, we talked about three different kinds of heat: transfer, convection, conduction, and radiation. That's just a different thing with the same term. Well, anyway, there are 4 different types of nuclear radiation, and I'd like for you to know the characteristics of all 4 of these. Here's the first one: alpha particles. Now, alpha particles are signified by this little symbol right here. It kind of looks like a fish and kind of looks like an A at the same time. I don't know if I can draw a good one here or not. But anyway, that's an alpha particle. That's the Greek letter A is what it is. Alpha particles have a positive charge. Now, here's why. Alpha particles are actually shooting out more than one item. You can see here that you have 2 red things, which is protons, and 2 blue things, which is neutrons. Now, if you have 2 protons and 2 neutrons, that's going to give you a positive charge, a charge of +2. I'll just use this plus sign that's right here. So, by definition, when you have 2 protons and 2 neutrons, what you have is helium that just doesn't have any electrons around it. So this is actually helium. Alpha particles are helium that is taken out of some other nuclei. That doesn't sound right. It's taken out of some other element, and literally helium is taken out of it. Now, that's something that you don't think you can just change elements like that. And if people could learn how to just change elements, gosh, the number of elements that would be turned into gold and silver would be phenomenal, and it would devalue that. But still, nature can do that. It can just make a helium and something else out of an original element, you might say. So by definition, these alpha particles, they're helium. Now, one thing about these alpha particles is they're large. I think your book is actually going to call them massive. And as a result of being so large, I mean, it has 4 things right here together, it's not going to be able to penetrate through much. Now, keep in mind, these nuclei are shooting these out of the nucleus. But these are not going to do much damage as far as its sheer destructibility, because it can barely make it through a sheet of paper. But what they do, if they are able to go through anything, they take electrons from whatever they go through. I mean, you got something with a positive charge. Ions with a positive charge tend to want to take on electrons. So that's exactly what it does. So what can happen, it can literally have one element that's changed into two, and then this helium that is shooting out can change other elements because it's taking electrons. It makes other ions. But like I said, it's not very, doesn't pose much damage because of its size, just because it's going to go through pretty slow. So as it's taking electrons, that slows it down, and like I said, it barely even goes through paper. Now, beta particles are signified by the Greek B. I don't know if I could really draw that very well, but it looks something like that with a long B tail. But anyway, beta particles are not shooting out protons and neutrons. Beta particles are just shooting out one electron. Shooting out one electron. And of course, since it is one electron, it is a negative charge. Now, these beta particles travel farther than alpha particles. They go faster. They are much faster moving. Now, you may be thinking, how can a nucleus send out an electron? There are no electrons in the nucleus. And that's a really good question. Here's what scientists think is happening. Scientists think that the neutrons, you know, it has protons and neutrons in here, think that the neutrons decay to form one proton and one electron. So the fact that it is decaying will end up changing the neutron to one proton and one electron, which still keeps it at a evenly charged inside the nucleus, because that's positive and negative. But then when that electron is formed, it's what will shoot out. So it's kind of funny how you could take something that doesn't have an electron in it, and suddenly an electron shows up. But anyway, this electron is ejected as a beta particle. Now, beta particles will go through stuff, and just like any other negative ion, it will want to take protons. Now, what happens when it takes protons? It's going to change the element. For example, helium here has 2 protons. If some ion coming from a radioactive nucleus takes one of those protons, by definition, it's not helium anymore. It would be hydrogen, because hydrogen is 1. So these can actually change what the element is that it goes through. And that's kind of strange. But anyway, these beta particles are faster than alpha, but they are stopped fairly soon. If you take 3 millimeters of aluminum, you know, that's not very thick. I mean, even if you were to put your finger and thumb together and put them as close as you can, that's probably in the ballpark of 3 millimeters of aluminum. And it's also 10 millimeters of wood, which is still just 1 centimeter, which is way less than an inch. But anyway, they'll pick up the protons from materials, and that's when they will lose their energy. So these kind of act similar, these alpha and beta. They don't go very far, but when they do, they pick up materials, either protons or neutrons, either electrons in alpha's case, or protons in beta's case, and as a result, they will slow them down. But now let's talk about something which can really damage things. Gamma rays. Gamma rays, the symbol for that kind of looks like a strange little Y. That's another, kind of like the alphabet in that alphabet there. But gamma particles, they're not made of matter. You can't say, oh, it's shooting out a proton, it's shooting out an electron, or it's shooting out helium or whatever, because what comes out is not really a particle. But scientists know that stuff comes out of it, and damaging stuff comes out of it. Since they're not made of matter, they have no electric charge. They are not positive, they are not negative. They are a form of electromagnetic energy. Hey, you've heard of electromagnetic waves before. Those are waves that come from the sun and do not need any medium. So sure enough, gamma rays do not need any medium. So they could go through a vacuum, and yes, they are very high energy. Very high energy. Now, they don't make ions like alpha and beta. So as a result, that doesn't slow them down. And yes, they can go through 60 centimeters of aluminum. That's a lot of aluminum. Now, we're not talking millimeters like we were here in beta particles. We're talking centimeters. So that's 600 millimeters of aluminum. So they're like 200 times more stronger, more high energy than beta particles are. Now, I have in my notes that also means they can go through 7 centimeters of lead. 7 centimeters of lead. And I'll put that here because it'll have to do with what's coming down below here. And of course, they do cause a greater health damage than alpha and beta particles. Another one is neutron emission. Now, you probably can figure out what's happening here. With alpha particles, it's sending out protons with the neutrons. Beta particles, it's sending out electrons. Neutron, of course, is sending out a neutron. So what's happening here, like this beryllium-13, it sends out a neutron and it changes it to beryllium-12, and there goes the neutron. So what effects does that mean? Now, neutrons, of course, have no charge. So it's not going to be positive, not going to be negative, and that means they're not going to slow down when they react with stuff like alpha and beta do. So they can travel up to 15 centimeters of lead. Now, I forgot to put centimeters here, but it was 7 centimeters of lead here. So neutron emission is around double of what gamma rays are. Pardon me, my phone's ringing in the background. I think one of my children can pick it up. If an unstable nucleus emits something, then you end up with formulas. And the formulas are down here at the bottom. Now, I'm going to run out of time if I hit too much on this, but you can see what alpha, beta, gamma, and neutron particles can go through up here. The paper didn't even mention plastic and concrete, but they're kind of in order. But what happens here is you have a new, these things sending things out are going to change the element. Here you have something called Pu, and I can't even remember what that is, but it sends out the helium and it changes it to uranium. That's an alpha particle right there. Here we have a beta. What's happening is you are sending out an electron, and this carbon form goes to nitrogen form. Here you have some kind of cobalt. Now, it doesn't seem to change it on this gamma, because this is indeed a gamma, because you're not changing the nucleus any. Well, you're changing nucleus because it's sending something out, but it's not going to make much of a change here. But here you have a neutron emission. Now, notice on the neutron emission, it does change the number of neutrons, so that makes it a different isotope there. So you can write a formula for each of these, and that's something that we'll end up having in class. Whew, I have not given myself a whole lot of time in which to talk about these half-lives. So why don't I talk about the half-lives on the next video. Hope you've learned a little bit about radioactivity. And hey, don't forget to read about this in your science book.